Good morning, everybody. Welcome to day 2 on week 2 of the semester. In yesterday's class, the last topic that we talked about was how to build Lewis dot structures, specifically for covalent compounds. So now as a review, we are going to go over the rules for how to draw Lewis dot structures, and then we're going to proceed to practice how to do this. Rule number 1 says that we are going to add up the total number of valence electrons for each atom in the molecule. We get the number of valence electrons by the group number, and this is specifically for things that are representative elements. Remember that your representative elements are going to live in group 1A all the way to 8A. Now, there's going to be times where we're going to be building these structures and they may have an overall charge, and that's going to be for the ones that are polyatomics. It could be ammonium, which is our positive polyatomic, or it could be any of the anion polyatomic ions that we have out there, the ones that have a negative charge. Understand that whenever we have something that has a negative charge, then we need to make sure that we add to the valence count that negative charge in terms of electrons. So if you have, for example, nitrate, which has an overall charge of -1, then you add 1 electron to the valence count. If you have something like carbonate, which has a -2 charge overall, you're going to add 2 electrons overall to the valence count. Now, if you have something like ammonium, which is a cation, then because it has 1 positive charge, then we're going to subtract 1 ion from it. Or sorry, not 1 ion, 1 electron from the valence electron count, okay? Number 2, we are going to write the symbol for the central atom. The way that we define the central atom, as you can see here, is going to be, it tends to be the atom with the lowest subscript. It is the one that is the least electronegative, but electronegativity is a topic that we will be dealing with later today. Understand that right now, from the concepts that we know, the most metallic, okay, is going to be defining what is going to be our central atom. Remember that metallic character, it is something that we talked about in class, and you do not need to be a metal, okay, in order to have metallic character. That's also true. The element that it is the furthest away from fluorine is going to be the least electronegative, because we're going to deal with electronegativity. But remember, things that are away from fluorine, you know, below in the periodic table, have a higher metallic character. So either way, that works. Now, we are going to attach all the atoms that we have in our chemical formula to that central atom. And we're going to do that by writing a line. That's what it means with use 1 pair of electrons. Remember that a pair of electrons, it can be symbolized by writing a line. There's 2 electrons on each line. Then we're going to count the number of electrons. We can subtract them to find the remaining. And then we have to remember that most atoms in the periodic table want 8 electrons. That's what the Octet Rule is. The reason why the Octet Rule exists is because, remember, many atoms in the periodic table want to achieve that noble gas configuration. Now, there's always exceptions to the rule. So understand that for this course, you're going to focus on 3 different situations in which these atoms do not want an octet. As you can see, the first one that we have is hydrogen. Because hydrogen is in period 1, it only needs 2 valence electrons to achieve the noble gas configuration of helium. So that's why it only wants 1 line, meaning 2 electrons to be shared. Boron, which is the next one that we have there, only needs 6 electrons, aka 3 bonds or 3 single bonds around. And lastly, beryllium. Beryllium only wants 4 electrons, aka 2 lines around it to achieve noble gas configuration. So understand is that not everybody wants an octet, okay? And specifically these 3. We also discussed in class how there are atoms that are going to be having expanded octets, but in this class, I don't want you guys to focus on the expanded octets. But for those students that are taking maybe other chemistry classes after Chemistry 104, understand that expanded octet means that those are going to be atoms that can hold more than 8 electrons. When we look at the periodic table, nonmetals that live in period 3, for example, phosphorus, sulfur, chlorine, those are going to be atoms that can actually hold more than 8 electrons. But I don't want you guys, at least for the purpose of this class, to focus on the expanded valency that some of these atoms have. Then, as you can see on rule number 4, if there's not enough pairs of electrons, okay, you need to start moving them, and that's something that we're going to see here. I will show it in the slide in a moment. What are going to be the number of electrons for hydrogen, boron, and beryllium? So when it comes to rule number 4, remember that at times, if our central atom doesn't have the 8 electrons that it may require, depending again, what is our central atom, then we have to bring electrons in from the surrounding atoms, and that's what's going to make double bonds and triple bonds, okay? But if by any chance the outside atoms, all of them have the number of electrons that they required, and you have extra, you stick them on the central atom. So, as you can see in the next slide, hydrogen requires only 2 electrons to form a noble gas arrangement. That's why whenever we see hydrogen for the most part in covalent bonds looks like this. It has only 1 line next to it. Beryllium requires 4 electrons to form a noble gas arrangement. So whenever we see compounds with beryllium, you can see that that's how it looks like. And then as you can see, boron requires only 6 electrons to form a noble gas arrangement. So we tend to see boron like this with 3 lines around it. Remember that each line represents 2 electrons. And then you see that the last bullet point is what I was mentioning with the nonmetals that can have an expanded octet, meaning that it can hold more than 8 electrons. But in this class, I'm not focusing in that last bullet point. This is just for students that are going to be, taking other chemistry classes, okay? So yesterday, we went over how to do specifically the Lewis dot structure for H2S, okay? Now, let's actually do a little bit of practice when it comes to this. So H2S, what is going to be the name of that compound? And again, we haven't done chapter 10, which is how we learn how to name it based on its ability to solubilize in water. But right now, what is the name for the chemical formula H2S? Let's review naming. Let's put it in the chat. What is the name for H2S? Great job. This is dihydrogen. But then I see that we're not giving the number of atoms for the sulfur. Yes, it is sulfide, but we need to put something before the sulfide. How many sulfurs do we have? Remember that the second nonmetal always gets a prefix. Excellent. Mono. sulfide. Okay, forgetting the mono will make, for example, this incorrect. So understand that we need that mono in there. Great. Now, let's go over letter B. So I'm going to do letter B with you guys. I had those highlighted just in case we had time to count the valence electrons, but I'm going to do letter B with you guys, at least the first part, where we're going to count the valence electrons. So when it comes to the valence electrons in the system, we have two atoms here. We have beryllium and we have bromine. We have one beryllium and we have two bromines. Where did I get those numbers from? From the subscripts for this compound. So each of these atoms, these are the subscripts. There's one beryllium and there's two bromines. Now, I go to the group number, okay? When it comes to the group number, beryllium lives in what group? Let's put it in the chat. Excellent. Thank you, Francisco. It is in 2A. So because it lives in 2A, it's going to have two valence electrons. What about bromine? Excellent. It's in 7A, so it's going to contribute 7 valence electrons. So we're going to multiply our valence electrons times the subscript. So beryllium is going to contribute 2 electrons to the system. In terms of bromine, it's going to contribute 14 electrons to the system. Once we get these numbers, we need to add them. Okay, so this compound has 16 electrons available for bonding. Okay, so at this time, I want you guys to take a few minutes and do C and D. Let's do the number of valence electrons for C and D. I'll give you a minute. Great job with those answers. So for letter C, sulfur, we have 1 of them. Oxygen, we have 3 of them. So sulfur and oxygen both live on group 6A. So each of them is going to contribute 6 valence electrons. In the case of sulfur, since we only have 1, this is going to equal 6. But in the case of oxygen, this is 18 electrons. So that means that in SO3, we have 24 electrons available for bonding. In the case of HCN, we have a hydrogen, a carbon, a nitrogen. We have 1 of each. We're going to multiply it times the number of valence electrons that they each contribute. Hydrogen contributes 1 electron. Carbon contributes 4 electrons. Nitrogen contributes 5 electrons. 1 plus 4 plus 5. There's 10 electrons in this system. Okay. Now, if we look at CO3 2 negative. Okay, so if we focus on these are negatively charged polyatomic ions. In the case of CO3 2 negative, we have carbon, we have oxygen. 1 carbon, 3 oxygens. Carbon contributes 4 electrons. Oxygen contributes 6 electrons. So we have 4 electrons from carbon. We have 18 electrons from oxygen. So at first, we're going to say that there's 22 electrons available for bonding. Now, because there is a -2 charge, we're going to add 2 electrons to our valence electrons count. That's because the overall charge is negative. So for carbonate, there are actually 24 valence electrons available for bonding. Now take a moment. Let's count the valence electrons for chlorite. Let's do the count of electrons for chlorite. What part do you need me to repeat? Why did I add 2? Excellent. So when we have polyatomic ions and they have a charge that is negative, we're going to add the value of that negative charge as electrons in our valence electron count. So in carbonate, because there is a -2, we're going to add 2 electrons, okay? Excellent.
So this is only for the one we have polyatomic ions, the charge is reversed. So it's a -2, it becomes a +2. We add that?
No, let me correct that in what you said. It's not that it becomes +2, it's just that we are adding electrons. Remember that electrons are negatively charged, so we are adding electrons to our electron count. See how that is just a plus? It means adding electrons. We are not making those electrons positive. So
thank you.
No problem. When I saw that in the chat, oh, there's another question. Excellent, exactly. The question in the chat is, if there was a +2 charge, then you will take 2 electrons away from the count. Exactly. So when it's positive, we subtract electrons, but if it's negative, then we add electrons to the count. So thank you for putting the answer for letter F on the chat. So here we have 1 chlorine, we have oxygen, there's 1 chlorine, there's 2 oxygens. For chlorine, we're going to multiply it times 7 electrons, because remember, chlorine lives in 7A. For oxygen, we're going to multiply it times 6 electrons, because it lives in 6A. So this is 7 electrons. This is 12 electrons. So at first, we're going to say, oh, there's 19 electrons available for bonding. But wait, here, because we have a negative charge, okay? So if you don't see a number there, it's because there's a value of 1. So then that means that we are going to add 1 electron to the electron count. So that's where the 1 electron comes from. And that's why in the chat, you could see that some students answer, oh, wait, there's 20 electrons in it, okay? Questions? Finding the number of valence electrons given a chemical formula when we are building the Lewis dot structure for a compound. Let me just check. I have 32 students. Put a 1 in the chat if you're solid on the idea of counting the valence electrons available for bonding. Excellent. I love to see those 1s. That the majority of you guys get that. Great. Okay. Now, when we are going through the process of building these structures, understand that, as I said, when we're trying to determine what is the central atom, at this time, you guys don't know electronegativity, but understand that the most metallic or the atom that has the most metallic character is going to be our central atom. We can also define it by the atom specifically that has the lowest subscript. So if we look at letter B, let's put in the chat what is going to be the symbol for our central atom. We only got two choices. It's either B or BR. Excellent. Beryllium is going to be our central atom. Okay. If we look at the periodic table, beryllium is all the way left. It's in group 2A. So it's going to have a higher metallic character than bromine. Okay. Now, rule number 2 also tells you that we are going to attach, utilizing a pair of electrons, the remaining atoms to our central atom. So we're going to put one bromine here and one bromine here. Now, let me specify something. Do I need to put these bromines left and right? Not necessarily. You can put them on top and in the bottom. You can put one to the left, one to the top. You can put one to the right, one to the top. There's a different combination of it. For me, in my experience of my chemistry training, I like to see my molecules symmetrical, that it looks about the same left and right. So that's why you see me writing them in a straight line, in a horizontal line, okay? So I just want to specify that just in case when you're drawing these, you're like, okay, but why is it that we typically draw it this way? This is just something that we in our training are accustomed to, because the majority of the instructors out there for chemistry, we use the same practices and we learn chemistry in a similar way. Now, you see that when I attach the bromines to the beryllium, I put 2 lines. Since I put 2 lines attached to the beryllium, how many electrons at this time are actually being shared between beryllium and bromine? Let's put it in the chat. How many electrons are being shared? Excellent job, 4 electrons. So because 4 electrons, because remember, a line means 2 electrons. So since there's 4 electrons being shared by the lines, then we're going to subtract 4 electrons from the system. That means that we have 2 electrons, 12 electrons left to put in this molecule. Now, we need to start getting the octets, okay? So whenever we're filling the octets in the atom, we need to do it from the outside atoms, and then we work our way to the middle, okay? So right now, if we treat, for example, the bromine on the left, it has 2 electrons which are being shared with a beryllium. So in order for bromine to get to 8, specifically, it needs 6 dots. 1, 2, 3, 4, 5, 6. So I utilize 6 electrons, okay, to complete the octet of the bromine. So if I use my highlighter tool, because we're just beginning with this concept, these 6 electrons are these 3 lone pairs that we have in bromine, okay? So at this time, I can only attach to this molecule 6 more valence electrons, okay? I need to make sure that my other bromine also have an octet, because as I mentioned a few moments ago, we need to try to get the octets of the outside atoms, and then we work our way in. So the bromine on the right also needs 2, 4, 6 electrons, and then the 8 are completed by the ones that are shared with beryllium. So at this time, we already used all my electrons available for bonding. Let me use my highlighter tool. So these 6 electrons are here. These 4 electrons are here. So my 16 electrons are being used, okay? Now, when I look at my molecule, in this case, my central atom, okay, is not an atom that requires an octet. So let me ask you a question. Does beryllium need 8 electrons? Yes or no? Y or N on the chat. Does beryllium need 8 electrons? How many does it need? Let's put it in the chat. Exactly. It doesn't need 8 electrons. How many does it need? Beryllium doesn't need 2. How many does it need? Excellent. It needs 4. Does it have the 4 that it needs? Excellent. So we're done with this Lewis dot. Beryllium is happy. It has the electrons that it needs in order to achieve that noble gas configuration. Bromine has the 8 electron that it requires to make that noble gas configuration. So this Lewis structure is done. Gina, go ahead with your question.
So my question, bromine is in 7A.
Yes.
So we're not, when we do the Lewis dot structures, we're not considering the periodic table, correct? We're just trying to follow the octet rule.
Mm-hmm.
Okay, and then for beryllium, when you said there's only 4 electrons, where that number, the 4 electrons, does that come from the chemical formula, the Br2?
No. So what I mean with the 4 electrons for beryllium is just that it has been shown experimentally, meaning in the laboratory, that beryllium, when you see it making compounds, because beryllium is weird, right? If we rationalize it, beryllium out of 2A is the only element that makes covalent compounds. Magnesium makes ionic compounds, calcium makes ionic compounds, strontium makes ionic compounds. Those are the cousins that live in the same group. Beryllium is the only one in there that makes covalent compounds. Now, furthermore, beryllium doesn't follow the octet rule. Beryllium only needs 4 electrons in order to have a noble gas configuration. Again, these are exceptions to the rules that I mentioned. So that's why when we rationalize what is the type of covalent bonds that beryllium needs in order to have its stability, again, that stability is how is beryllium achieving that noble gas configuration is by sharing 4 electrons. Now, another part of the question that you just asked, I know that students, depending on who your instructor is in the past, have gotten students used to the idea of, oh, when you're building Lewis dot, you write the Lewis dot for every atom, and then you start connecting the dots. I actually don't like that approach into building Lewis structures, because the problem is that when in your Lewis structures, you have to generate double bonds and triple bonds, that approach makes the whole idea of building Lewis structures a little bit more complex. So I'm giving you generalized rules that are going to help everybody. There's a question in the chat. How did you know that bromine need 3 sets of dot? And like, how do you know where to put the dots? Excellent question. So the majority of the elements in the periodic table want 8 electrons. So for the purposes of this course, what you need to keep in mind is hydrogen doesn't want 8 electrons, boron doesn't want 8 electrons, beryllium doesn't want 8 electrons. Those are the only 3 exceptions that I'm introducing to you guys. Every other atom in the periodic table wants 8 electrons. Now, taking that into consideration and looking at those exceptions, hydrogen only wants aligned because hydrogen only needs 2 electrons. Beryllium, as you can see, only needs 2 lines, aka 4 electrons. Boron only likes 6 electrons, so 3 lines. Every single one of the other atoms that you encounter needs 8 electrons. No problem. So the octet rule is a rule that establishes that the majority of the atoms in the periodic table want 8 electrons because having 8 electrons makes them have a noble gas configuration. As we mentioned in class yesterday, remember that in terms of the atoms, what the elements in the periodic table look up to is the elements that live in 8A, meaning those elements that have a full valence shell. Why is it that atoms want to achieve noble gas configuration? Because remember that having a full valence shell gives you stability. That's why in class yesterday, I mentioned to you guys, it's kind of like, if we utilize the analogy of you as a person, if you need to look up to somebody, you want to, at times, have the stability of that person. So when you look up to somebody, it's because you want to achieve that stability. At the atomic level, that means that as an element, I want to achieve stability. Which are the elements that have stability? The ones that live in 8A. As you guys know, elements in 8A are going to have 8 electrons in their valence shell, except helium that only has 2, and that's why hydrogen, because it's in the same period, only wants 2. But that's the reason why we call it octet rule. Is that more clear? Awesome. Let's try now the Lewis structure for SO3. What is the name of SO3? Let's put it in the chat. What is the name of the compound SO3? It's not sulfite. Excellent. It's sulfur trioxide. The difference between sulfur trioxide and sulfite is the -2 charge. So understand that in exams and quizzes, if you don't see that -2 charge, don't assume, oh, Dr. Luz forgot. Let me remind her that I know this to the dot and that there's a -2 charge that she didn't write. I did not forget the -2 charge. Remember, SO3 is also a compound. Okay, so SO3 is sulfur trioxide. If you see that -2, then that is sulfite. And what would be the difference in valence electrons between sulfite and sulfur trioxide? Exactly. Thank you for putting in the chat. 2 electrons. While sulfur trioxide has 24 electrons available for bonding, sulfite will have 26 electrons available for bonding because of the -2 charge. So it does make a difference, you guys. Make sure that you keep track of those things. You know, I am not a perfect human. At times I make mistakes, but understand that when I make mistakes, I will let you know, like, hey, you guys, this is a mistake. But when it comes to this, like, in we are learning chemistry, understand that what is written, for the most part, unless I correct myself, it is what you're working with. So taking into account that we have sulfur trioxide, right? Sulfur and oxygen are in the same group, okay? They're in group 6A. So who is more metallic, sulfur or oxygen? Meaning, who is the central atom, S or O? Let's put it in the chat. Who is our central atom? Great job, that's sulfur. So sulfur is going to be our central atom. we already know that there's 24 electrons available for bonding. Now, here, remember, rule number 2 tells you, use a pair of electrons and attach the other atoms that you have to the central atom. So again, for space purposes, I'm going to attach an oxygen here, an oxygen here, and an oxygen here. Again, for space purposes. If you put the oxygen, you know, one on top, one on left, one on right, that's okay also, okay? So taking this into consideration, how many electrons did I utilize to build this structure? Excellent job. I used 6 electrons in the system, so I have 18 electrons left, okay? So taking this into account, again, I'm going to fill the octets of the outside atoms in. Each of the oxygens are sharing 2 electrons with the sulfur. So each of the oxygens needs 6 electrons to complete their octet. So I'm using 2, 4, 6, 8, 10, 12, 14, 16, 18. So my 18 electrons were used by putting the lone pairs on my oxygen. So these 18 electrons are here. These 6 electrons are these. As I mentioned to you guys a few moments ago, for the purposes of this class, everybody wants 8 electrons except hydrogen, beryllium, and boron. So sulfur is not happy because it doesn't have 8 electrons. Okay? So how do we give sulfur its octet when we have used all the valence electrons in order to complete the octet rules of the outside atoms? Well, we are going to make one of the oxygens share in with the sulfur. And then that's how you make a double bond. Excellent in the chat. Now, which oxygen is going to share in the sulfur? That's up to you. It could be the one on the left, it could be the one on the right, it could be the one in the bottom. It really doesn't matter, because ideally, understand that you can draw 3 different structures for this sulfur trioxide. One in which, as you can see, I'm just going to erase these 2, and then I'm going to put them here and share them in with the sulfur, okay? Now, I could have done that with the oxygen on the right. I could have done that with the oxygen in the bottom. If you write any of those 3 different sulfur trioxide structures, that's what we called in chemistry resonance structures. They're going to be contributing structures to the overall Lewis dot structure for a particular molecule. Now, resonance structures is something that is not in the textbook. It's not something that we do constantly in this class. I just want to mention this concept for those students that have other chemistry classes after Chemistry 104. The resonance structures is spelled like this. So resonance structures is going to be multiple Lewis dots that represent the overall Lewis structure for a particular molecule. So this SO3 will have different resonance structures, and resonance structures are written in a particular way. Again, it is not discussed in this textbook, but understand that that's how it is. I'm going to erase that because I'm not going to test you on it, okay? So now, every single atom in SO3 has 8 electrons, and we have utilized the 24 electrons available for bonding. Any questions on letter C?
I thought that sulfur needs 6 electrons. Why is it 8?
Where did you see that sulfur needs 6 electrons?
Because when we did the calculations, it's like 1 times 6 is 6.
No, sulfur doesn't need 6 electrons. Sulfur is contributing its 6 valence electrons for bonding in the Lewis structure. Sulfur wants to have a 8 electron sharing system to achieve noble gas configuration. So that is very different. What we're doing with the calculations on the left is saying, let's just use an analogy, right? Here, there is 2 people. Let's say that there's 2 people going on a date, right? Sulfur and oxygen. Sulfur can only bring $6. Oxygen can bring $18. So the electron count is what are you bringing in to the date, or what are you bringing in to this structure that you're trying to build? So you can see that oxygen, because it has a subscript of 3, is actually bringing more electrons into this structure.
Okay, thank you.
No problem.
For sulfur,
Yes.
like
Gina, I couldn't
the-
hear your question. Could you start again? Because it was getting choppy.
is it better? Can you hear
Yes.
me now?
Yes.
Okay. You know, yesterday you said that the central atom is always the one that has more metallic character.
Mhm.
Well, if we're going across a period, oxygen and sulfur, the oxygen is 1 period above sulfur, but they're in the same group. So how do you know which one would be your central atom?
So remember that we have trends in the periodic table for when we're going across a group. We also have trends in the periodic table when we're going and comparing things within a group. So metallic character, when you're comparing things that are in the same group, meaning the same period. So when we're looking across left to right in the periodic table, establishes that metallic character decreases as we go left to right. Meaning we start with the metals, we're going towards the non-metals, so the metallic character is decreasing. In the case of sulfur and oxygen, they are in the same group. It established, if you look back at the notes, that metallic character increases as you go down in a group. So because sulfur is below oxygen, it has a higher metallic character compared to oxygen.
I got it now. I was just confused. Like I said, they're in the same group, so I wasn't sure why we chose sulfur over oxygen, but I thought that was the reason, but I just wanted to clarify.
Okay, no problem. There's a question in the chat. Is there a difference between valence electrons and the number of electrons needed to complete the outer orbital? I imagine that's what it is. The lowest number of subscript is the central atom. Yes, okay, so that was for the question that it was. But so is there a difference between valence electrons and the number of electrons needed to complete the outermost shell, aka the valence electrons in an atom? Okay, so remember that when we're dealing with covalent compounds, okay, the goal is that if you are bringing a certain number of valence electrons, you're going to start sharing other atoms' valence electrons. So we are all, as an entity, having 8 electrons in, depending, on the atom, but the majority of the atoms want to have 8 electrons. So as I was mentioning, if you look individually at the contributions of everybody, sulfur brings And this is why sometimes these things are complex if we see it the other way. So some students learn that, oh, what you need to do is that you say sulfur has 6 valence electrons. Oxygen has 6 valence electrons, and we have 3 of them. Again, this is not my favorite way to explain this. I'm just doing it because it may help somebody. Okay, so this is at the individual level. Okay, how they're coming. Let's say that these 4 atoms are trying to build a company, are going to start to make a business, if we want to use an analogy, right? So here, each atom individually is bringing 6 valence electrons. But again, we're trying to be entrepreneurs. We're trying to build a business. So we need to share. And in the sharing, we want everybody to have, let's say, equal pay or equal amount of what we're earning out of our business, right? In terms of the atoms, that means that we are going to be happy because of the atoms that we're dealing with when everybody has 8 electrons in it, okay? Now, the only thing about this compared to the structure that I did is that it is kind of complex. How do I explain double bonds? So in the structure that I drew, it explains how we are all sharing electrons, okay? And how some atoms are going to have lone pairs, meaning those are non-bonding pairs, in order for everybody to have 8 electrons. In the structure of sulfur trioxide, what is happening overall is that there's 1 oxygen that is sharing 4 electrons with sulfur, and it's having 2 non-bonding pairs, meaning 2 lone pairs. The other 2 oxygens share 2 electrons with sulfur, and they have 3 non-bonding pairs, meaning 3 lone pairs. Sulfur in this structure needs to always share electrons with the atoms around them, okay? So the valence electrons are going to be the ones that need to be, in this case, shared, okay, in order for this team to actually come together and make the structure for the molecule, okay? So what we're doing here is explaining how is it that the atom's valence electrons come together to make the structure for the molecules that we're interested in. The molecules that we're looking at is specifically covalent molecules. Does that answer your question, Victoria? Because not all the electrons are involved in bonding. It's only the valence ones. The core electrons are not involved at all. No problem. Now, let's do a little more practice when it comes to this. We have several more. Here we have HCN. There's a question in the chat, okay? The double bond could be between any oxygen as long as you're removing the 2 dots on the oxygen. That is correct. Any oxygen needs to can contribute to the middle one. And remember, if you're sharing them in, you need to erase it, okay? From the atom that is going to share it. And the way that we share it is that we just now share them as a line. Let's go to HCN, okay? Now, the rule of the atom with the least subscript doesn't apply to this molecule, okay? So if we're comparing hydrogen to carbon to nitrogen, which one is the most metallic? Meaning that it has a higher metallic character. Excellent, carbon. Because remember that for metallic character, hydrogen is sitting next to helium, okay? It's not part of 7A, it's just sitting there where 7A is there. So carbon is our central atom, okay? Now we are attaching the rest of the atoms to our central atom. So here is nitrogen, here is hydrogen. How many electrons did I use to make this starting structure? Excellent, 4 electrons. I'm just going to stop highlighting the bonds. I hope that you guys can track. So there's 6 electrons left, okay? I'm going to start, again, building the octets on my outside atoms, and the last one that I'm going to build, the octet, is the central atom. So how many dots does hydrogen get? I disagree. How many dots does hydrogen get? Thank you for the people that put none or 0. Hydrogen only needs 2 electrons. It only has 2 electrons. No, it already has 2 electrons. It doesn't need 2. It already has 2. The line is the 2 electrons. If you put 2 dots, if you do this, which is incorrect, if you do this, how many electrons now hydrogen has? If I do that. Exactly, it has 4, so it can't do that. The line is enough. So hydrogen doesn't get any dots. Now we're going to the nitrogen. In order for nitrogen to achieve its octet, how many dots do I need to put on them? How many dots do I need to put on nitrogen? Excellent. 1, 2, 3, 4, 5, 6. So I use all my dots, okay? I don't have any more. So carbon is sitting in the middle. Is carbon happy? Does carbon at this point have an octet? Exactly, carbon is not happy. Carbon is looking to the side and to the other side. So this is like you and your buddies go out and you're in the middle, and all of a sudden there's a cover charge for you to go into the club, and then you look at hydrogen and hydrogen is like, bro, there's nothing that I can share with you. I'm already sharing. Nitrogen, on the other hand, you're like, you're carbon, right? You're like, yo, nitrogen, I need electrons. Exactly. So carbon needs 4 electrons to achieve its octet. Who is going to give those 4 electrons that it needs? The nitrogen. We're going to erase 2, and now we're going to share them with carbon. And that's what gives rise to a triple bond. Any questions on letter D?
Yes. Sorry, Professor. I feel like I'm asking a lot of questions. This is a harder concept. I don't know why it's so much harder. So carbon, again, is our central atom. I get the bonds. I understand the bonds. It's more of the central atom I'm confused on.
Mm-hmm.
So as we go lower on the periodic table and more right, I guess you could say. Sorry. We have more metallic character.
No.
So would it no. Okay.
So remember that, where do the metals live? Left or right?
Left.
Exactly. So as we move right, we're going into things that are least metallic, right?
Non-metal. Oh, yes. Okay.
So let me just show the periodic table. Hopefully this will help. So if we look at the periodic table, right, we have several ones. This is from chapter 4. Let me look at the blank one. I know that we have a blank one here. Oh, right here. So as I mentioned in class, when it comes to metallic character, basically hydrogen lives here, right? It is a non-metal, so we have to set it there. Now, for this problem, we are comparing carbon, nitrogen, and hydrogen, okay? So when it comes to metallic character, the things that are in the second row are going to be more metallic. So that kicks hydrogen out in terms of the race for the most metallic. Are we good with that?
Yes, Professor. Yes. So
No problem. So
so you're telling me anything on the right side of nitrogen is no longer being considered, right? Is that what I'm?
exactly. So hydrogen is out of the race. Now, remember, if you're more left, you're more metallic, right? So when we compare carbon and nitrogen, then who is more to the left, carbon or nitrogen?
Carbon.
Exactly. So that's why carbon is in the middle. Most metallic sits in the middle.
Got it. Okay. I kind of understand. And like I said, it's just the central atom, and I want to make sure when we're doing the Lewis dot structures that, because I know you're going to count towards which central atom we're putting. So I want to get that concept. So again, the only reason we're choosing carbon is because obviously it's closer to being, the more central the atom is to the middle, because obviously in the middle there's metals, is what we're considering over nitrogen, which is more like non-metal, like going toward, even if it's not a non-metal, it's more non-metal.
So let me correct what you were saying, Gina. We're trying to get we're trying to get the central atom that is the most metallic. So if we're talking about things that are in the same row, right, which is this case, carbon and nitrogen, whoever is more to the left will be the central atom. At first, we were comparing things that are top and below, right? And then
yes,
hydrogen, let's just put it this way. This is something that you guys will get used to the more practice you have. Specifically next week, you guys have a Lewis dot structure lab that is going to be like a worksheet. So it's similar conceptually to lab 4 because it's a worksheet based. So it's a lot of problems. So this will, all of this will solidify to you guys. Hydrogen will never be the central atom. Hydrogen, let's just put it there, write it in your notes because that is true. To date, in my years of studying chemistry, and I started taking chemistry classes back in '99, we have not seen a molecule in which hydrogen is the central atom, simply by the fact that hydrogen only wants to share 2 electrons, okay? So taking that into consideration, and thank you for the students that are answering questions in the chat. When you're comparing things, and hydrogen is one of them, please take hydrogen out of the race, because hydrogen never tends to be the central atom, simply for the fact that it is, it only wants 2 electrons in general. Now, when it comes to the other things that you're comparing, if you have elements that you're comparing them because they are in the same period, meaning in the same row, left to right, whatever is more to the left will be the central atom because it's the more metallic. When we do electronegativity, which is the concept after we finish all of this, then in your brain, you can click and say, you know what? The one with the lowest electronegativity will be the central atom. Those are the 2 ways to know who's central, either electronegativity or metallic character. It's just that right now, metallic character is the only thing that we have talked about. But once we talk about electronegativity, think about it. Least electronegative or more metallic, which means the same thing, is going to be your central atom. So that is the general rule. It's just that right now, again, because metallic character is the only thing that we're working with, it's what is in there. But when it comes to H2, H2 is a diatomic molecule. It's not that hydrogen is the central atom, it's hydrogen bonded to hydrogen. So that is a linear molecule. So it's not technically the central atom, it's just one of the two atoms that are in there. So H2 is just, again, that is a little bit different because we are looking at a hydrogen bonded to a hydrogen. So is it central? Well, that molecule is just symmetrical. So going back to any questions on D? Excellent. Let's go through E. Let's at least finish all these Lewis structures before we go on break. We only have 2 more to go. We have carbonate and chlorite. So when we are comparing carbon and oxygen, and let me just bring back the periodic table. Who's the central atom? Excellent. Gina, does it make sense why we pick carbon?
Yes, because carbon is more towards the middle than oxygen is.
Don't say middle, say left.
I'm so sorry. It's
okay.
more towards the left
Yes.
than oxygen is.
Because remember that in terms of the periodic table, metal is your transition metals. So
well, you know what? I just thought about it like this. I forget that everything on the right side of boron, aluminum, and silicon are non-metals. So it only makes sense that carbon is more metallic than oxygen.
Okay, so let me correct what you just said. Out of the elements that you just said, aluminum is a metal. Boron and silicon are going to be metalloids.
Metalloids. Sorry, I meant. I'm sorry, pregnancy.
So it's kind of, so if we think about it and rationalize it, it's a little bit on the weird side, right? Because if you look at period 2, right, where you have lithium, beryllium, boron, carbon. So you have metal. Beryllium is a metal, but it's weird within its class because it's the only one that does covalent bonds. Then we go metalloid, and then we go non-metal, 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 right? All the way to neon. So from carbon to neon, they're all non-metals. But within metallic character, which again, metallic character, it doesn't mean mean that you're a metal or more metal. Metallic characters means how willing are you to lose electrons? That's what metallic character is in terms of definition. If you're more towards the left within the same row, then you have higher metallic character.
Yes, I understand now. Thank you, Professor.
No.
I was just, like I said, that concept was a little difficult for me to understand, but I get it now. Thank you.
No problem. So we have carbon in the middle. And then I have the oxygens here. Again, I put the oxygens like like this, just because I choose to draw them this. You can draw the oxygens left, right, down, whichever way, up, down, left, up, down, right. I choose this in terms of space, okay? So, oh, that top oxygen. Let me just redo it. Better. Excellent. So I connected all my atoms to my central atom. Okay, how many electrons did I use? Excellent. 6 electrons. So there's 18 electrons that I'm going to need to incorporate here. I need to fill the octets of the oxygens first. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I already used my 18 electrons in the system. Okay. Am I done? No, there is one atom in my system that doesn't have 8 electrons and it needs 8 electrons. Which atom doesn't have 8 electrons and needs 8 electrons. Excellent. My carbon. Where am I going to get those electrons to give to carbon? Excellent. From oxygen. Which oxygen? Exactly. Any of them. So CO3 is another one of those molecules that is going to have resonance structures. So you can propose any of the 3. Okay. So I'm going to choose to erase these 2 and share them in. Okay. And this is the Lewis structure for this molecule. Now, for any student that needs to take other chemistry classes in the future, whenever we have polyatomic ions, we typically put them in brackets, and outside of the brackets, we put the -2 charge. Okay. So this is for polyatomic ions. We tend to put them in a bracket, and then we put outside of the brackets the charge overall. Okay. So just in case if you see this in the future, then understand that that is why that is like that. So I'm going to give you guys 2 minutes for you to do the Lewis structure of chlorite. Okay, so I'm going to give you 2 minutes to do the Lewis structure of chlorite, and I will go through it. So there's a question in the chat about what about the charge that we put outside. Understand that as long as you have a polyatomic ion, you put them in brackets and then you put the corresponding charge for it outside. It doesn't matter if it's positive or negative. So let's deal with chlorite, okay? My central atom for chlorite is going to be chlorine. The oxygens are going to be attached to it. This took care of 4 electrons. I have 16 electrons left in the system. Okay. Now, when it comes to this, we are going to fill the electrons of the oxygen atoms. 2, 4, 6, 8, 10, 12. Okay, so again, with the dots, I already used 12 electrons. So I have 4 electrons left. Who gets those extra 4 electrons? The chlorine. And then I look at my molecule, everything has an octet. So again, I'm going to put this in brackets just because this is a polyatomic ion, and I'm going to put the -1 outside. Questions on how to build Lewis structures? Excellent. Since there are no questions, I think it's time for a break.